Hello, everyone. This is the second pre-class video on quantum computation in INT Summer School. Did you enjoy the first video? In this video, I'm going to talk about the quantum simulation of the one-dimensional transverse Ising model. This is the plan of the talk. First, I will construct a time evolution operator in the Ising model. Next, I will construct the vacuum or ground state in the Ising model by quantum algorithm. Finally, I will give a summary and some announcements. Okay, let's move on to the time evolution operator. Here, I focus on 1 plus 1 dimensional trans-Ising model, whose Hamiltonian is given by this. Here, xn, yn, zn mean the Pauli matrices at site n. First, we have the nearest neighbor interaction, transverse magnetic field, and longitudinal magnetic field. Here, for simplicity, let us take n equal 2 and m equal 0 for a while. In this special case, Hamiltonian is explicitly given by this. Now, let's construct the time evolution operator, exponential minus iht, in this system. This time evolution operator describes the time evolution of any state. So this is very important. By using hx and hzz, this is explicitly given by this operator. Now, question is, how do we express this operator in terms of elementary data, such as x, y, z, rx, ry, rz, and control x, and so on. At the first step, we use a so-called Suzuki-Totta decomposition for this operator. This is the identity by using the large positive integer m. Then when m is very, very large, the time evolution operator can be approximated in this way. So let us use this approximation. So now the problem is reduced to realize these operators one by one. Note that the first one is trivial if you remember the definition of Rx. But the second one is non-trivial since this involves the product of two sets. And by definition, this is given by this operator. But one can show that this operator can be written in this way, by a combination of controlled x and rz. Here is the proof of the identity. We can explicitly check this identity by looking at the two cases acting on 0 psi and 1 psi. It seems a bit tedious, but we can explicitly check the identity is correct by using the definition of controlled x and rz. So this identity is correct. This is a quantum circuit for the time evolution operator for one-time step. First, we have exponential minus ihzz by the combination of the controlled x and rz. Second, we have the contribution from transverse magnetic field. But this is correct up to this order because of the Suzuki-Totta approximation. Once we get the time evolution operator, we can study a physical problem, which is a survival probability of free vacuum. For j equals 0, the Hamiltonian does not have an interaction, so the ground state is simply given by this state, which is a product of H0. Now let us compute the survival probability of the free vacuum under time evolution operator by full Hamiltonian. And this problem is a kind of toy version of the Schwinger effect. By using this identity, we can relate the survival probability like this. Therefore, we can compute PT by measuring the probability having 0, inside this state. All right, let us compute this quantity by using Suzuki-Trotter decomposition for this parameter. And this is a quantum circuit for time evolution operator for one-time step. We can easily compute this by using IBM quantum experience by making this quantum circuit by drag and drop. First, we are constructing the free vacuum by multiplying the Hadamard gate. Then we are acting the time evolution operator by using Suzuki-Trotter decomposition. And then we come back to the state 0 by multiplying H again, and then make measurement. This is the result by simulator with 1024 shots. We see that the free vacuum mostly survives. This sounds reasonable since we have taken t to be very small, namely t equals 0.1. Here is a comparison of the results by simulator and the real quantum computer. We see some differences, and these differences should be understood as a quantum error. So far, we have considered only one-time step. If you'd like to do more serious computation, we have to repeat many time steps. But it is quite tough to implement this by using IBM quantum experience. For that case, we need to implement this by using Python. And we will do this in the class. And this is the result of the serious computation in these parameters. So as we increase time, we basically have a decay of the free vacuum, but there is some restoration after some time. This is because of a finite volume effect. Here I finished the section on time evolution operator. Next, I will discuss construction of the vacuum in the transverse Ising model. There are various algorithms to construct the vacuum. Here, I adopt an algorithm called adiabatic state preparation. There are 3 steps. First, we choose an initial Hamiltonian H0 of another system. This is usually chosen to be Hamiltonian of a simple system so that the vacuum is explicitly known and unique. Second, we introduce an adiabatic Hamiltonian HAT satisfying these conditions. In initial time, HA should be H0. In the final time, HA should be the Hamiltonian of the target system. Also, derivative of HA should be very small when the parameter T is very, very large. Finally, we use a so-called adiabatic theorem. The adiabatic theorem claims that if HAT has a unique ground state with a finite gap for any T, then it is known that the ground state of the target Hamiltonian is obtained by this time evolution. All right, let us apply this algorithm to the transverse Ising model. Here is the Hamiltonian of the Ising model with a longitudinal magnetic field. Here, we choose the initial Hamiltonian to be this one. We have only the transverse magnetic field. We know that the vacuum of H0 explicitly by this, the state plus plus plus. Then we take the adiabatic Hamiltonian HAT to be this function. You can check that HAT smoothly interpolates H0 and the target Hamiltonian. In practice, we need to discretize the integral in the time evolution operator by this. Here, UT is a time evolution operator with very small time step. Once we get the vacuum, we can compute the vacuum expectation value of operators. In the Ising model, it is easy to compute the magnetization defined by this. If we insert the complete system here, then we can rewrite the magnetization by using a combination of finding each basis inside of the vacuum. This is for longitudinal magnetization. If we want to compute the transverse one, this is a bit more tricky, but we can compute it by using the Hadamard gate in this way. Since we already learned how to construct time evolution operator by using the Suzuki-Totta approximation, so we can construct the vacuum by adiabatic time evolution operator and then compute the magnetization. Here is the result by simulator in this parameter, and we will do this in the class if you have a time. This is the dependence of the magnetization as a function of the adiabatic time. The blue line represents the result by exact diagonalization, so this is the correct result. The red one shows the result by adiabatic state preparation. We see that as we increase time, the magnetization approaches the correct result. This is the result for two-side Ising model. Here is the result for other values of n. Similarly, we see that the result of adiabatic state preparation approaches the correct value as we increase the adiabatic time. Finally, I have some comments on adiabatic state preparation. It is known that the systematic error of adiabatic state preparation behaves like this. Here we have a capital T, which is the finite time of the time evolution, and the energy gap of the system. So this implies that if we want to study a system with a smaller energy gap, we have to take a larger T. There are both advantage and disadvantage of the adiabatic state preparation. First, for advantage, adiabatic state preparation is guaranteed to be correct for very large T and very small delta T, if we satisfy the assumption of the adiabatic theorem. Also, in the adiabatic state preparation, we can directly get the excited state under some conditions. There are also some disadvantages. First, if we do not satisfy the assumption of the adiabatic theorem, we cannot use this algorithm. So it does not work when the vacuum is degenerate. Also, this algorithm is known to be costly, meaning that this algorithm requires to use many gates. So this implies that the adiabatic state preparation is perhaps not so efficient unless error is negligible. Let me summarize. Here, I have considered the one-dimensional transverse Ising model And we constructed time evolution operator in the Ising model by using Suzuki-Trotter approximation. Next, we constructed the vacuum of the Ising model by using the adiabatic state preparation described by this time evolution. Finally, to use the algorithm, we require that the adiabatic Hamiltonian HAT has a unique ground state with a finite energy gap for any t. Here are some announcements. First, please install the Python module called QuizKit to your PC before the class. Next, pre-class assignment will ask some implementation of some computation in IBM quantum experience. The first class will be on some basics on using QuizKit. The second class will be on quantum simulation of the one-dimensional Ising model. Finally, the class will not discuss quantum field theory stuff, but if you are interested in this stuff, please look at another slide which I will upload on the Slack. This is the end of the second video, and continue to the class. Thank you for watching. Bye-bye.